Bam! Mr. Tarrou. In this math lesson, we're going to do an example of finding the volume of a parallelepiped using the cross product and dot product of vectors, those two operations with vectors. Instead of just giving you the formula for this and just running through it and maybe not having you completely understand the geometry of what's going on, we're first going to take a look at an older geometry question that you should be familiar with and show you the relationship between finding volumes of prisms or oblique cylinders, or maybe even right cylinders, whatever. Do a little bit of work that we just learned with vectors, like the cross product of vectors, the magnitude of that cross product of vectors, what does that represent, working with some trig functions, and develop the formula that we're then going to use ultimately in our final and most important example about the new stuff. How do you find the volume of a prism or cylinder? Well, you find the area of one of its bases, the two bases with a prism or cylinder are the same shape, then multiply by the height. So the area of our base, of course, we have a diameter of 10, so we just work through the fact that, of course, it's pi r squared, so pi times half the diameter squared. And then because of the fact that this cylinder is oblique, now I've given us an angle that's on the unit circle, but maybe you'd have to do a little bit of trig to figure out the height of this triangle. So we're going to put off a perpendicular that goes to or measures, the height of this cylinder. We have a leg here that, of course, begins or ends, however you want to talk about it, at the base. And we want the height, which is an adjacent leg to our 30 degrees here, and work with the hypotenuse of this right triangle of 14. So we would have that the cosine of 30 degrees is equal to adjacent over hypotenuse, and see that the height of this oblique cylinder is 14 cosine of 30 degrees, which, if you know your unit circle, you should be able to just write an answer, but I'm trying to really relate the new with the old that we already understand. So I'm going to leave this as 14 times the cosine of 30 degrees. So our volume comes out to be 175 square root of 3 pi square cubic units. Now, let's go over to the new stuff. This is still basically a three-dimensional figure that has the top and bottom plane are the same base, just like a cylinder or prism would be. So we're going to find the area of the base. So our volume here is going to be area of the base times the height. Okay, now we just learned a formula for finding the area of a base, or the area, which in this case is a parallelogram, that has two sides that are defined by vectors. The area of the base is the magnitude of the cross vector, or the vector cross product of vector u and vector v. Okay, well, we just did that in our last lesson, yes. So we understand how to do that, but you're not going to see the magnitude of a vector cross product in your formula for a volume of a parallelepiped. So what is going on there? Well, what's going on is, you know what? We have to find the vector cross product between these two vectors. So let's just remember, that is a new vector which is orthogonal to the two vectors that you did the cross product with. So we have vector u and v here. Let's draw what would be an orthogonal vector to those two vectors. And remember that this is vector u crossed with vector v, and if you happen to change the order of that, you're going to have the opposite of vector u crossed with vector v, or it is the vector cross product of v and u. So you want to be careful when you do the vector cross product or the vector product that you have the order the same as, whatever's given to you in the particular question. And we're going to talk about how to deal with the fact that we have a sign change for the difference in order for that vector cross product. But if I remember that this cross product is another vector which is perpendicular, or orthogonal, I should be saying, to these two vectors, well, then we're going to have an angle here, theta, that we could set up just like we did over here, a little triangle, and I need to pick a different color. Let's go ahead and use green. And we want the height, we want the adjacent leg, an adjacent leg in this little right triangle that's going to define the height of this parallelepiped. Okay, well now look at what we had over here, of course, that I've now erased. But that height was equal to 14 times the cosine of the angle between that length of that line segment and this vertical line segment, which we're going to use to measure the height. Well, that length of that line segment is effectively a magnitude of, you know, a vector is just a directed line segment, So here, this would be like our 14 for the cylinder. So our height, that's going to be the magnitude of this vector W times the cosine of theta, where theta is the angle between this vector W and the vertical vector, or the vector which is orthogonal to the base. You know, this base doesn't have to be horizontal. It just has to have all this relationship here where we have this orthogonal nature between, where we have this orthogonal relationship between our vector cross product and vector u and vector v. Okay, look at what we got going on here. The volume of a parallelepiped is therefore the magnitude of the vector cross product times the magnitude of vector w times the cosine of theta. But that's still not going to be what you see in your textbook for the formula for finding the volume of a parallelepiped. No, what it's going to say is this. It's going to say it's the dot product of the vector cross product dotted with vector w. Well, where did the cosine of theta go, and why is there no magnitude notation around our cross product? Well, if you remember your two definitions for dot product, there was an algebraic one which you used when your two vectors were in component form, and a geometric definition for your dot product. Pausing to make sure I said the right thing. And it said that, let's say, vector A dotted with vector B was equal to the magnitude of vector A times the magnitude of vector B times the cosine of theta. Well, that's what we have going on here. And there's some stuff going on inside of this magnitude notation, but it's a vector cross product, another vector. So it's the magnitude of one vector times the magnitude of another vector times the cosine of theta. So that's the geometric definition of your dot product, and that is why maybe when you look at a question like this and you haven't seen the formula for a volume of a parallelepiped given to you, you can still get to that formula on your own as long as you recognize or remember your two definitions for a vector dot product. Yeah, so this pattern is the dot product between these two vectors. So we're not going to look at the magnitude of the vector cross product of u and vector of u and vector v. We're just going to simply work with that vector, the cross product, the vector cross product of those two, and dot that with w. Now, your book may have a little footnote here that we do something else when this angle theta is obtuse, and other books may just say, you know what, hey, if you look at these vectors which are defining the base of this parallelogram, the order which you do that vector cross product is going to change just the sign of your answer. And originally we just wanted the magnitude of that cross product. So we're just going to come through here and take the absolute value of this to make sure that our volume comes out to be positive, and this is your formula for finding the volume of a parallelepiped. So I hope I've helped deepen your understanding, see the connection between your cross product, your magnitude, and your dot products that you've been learning through this vector lesson, and not just throwing a formula out here. So this isn't a proof, but to show you the geometry and the basis of where this formula is coming from that we're about to use in this example coming up right now. No. The diagram shows a parallelepiped ABCDEFGH, and given that the coordinates of vertice E is 5, -3, 1, 5, -1, 3, vertex F has the coordinates of 6, 2, 4, G, coordinates of 1, -2, and 3, and then finally A is got the coordinates of 6, 0, 5. Let's go ahead and find the coordinates of the coordinate of another vertex or vertice of this parallelepiped, and then we're going to find the volume. Now, we have the request, which is to find the coordinate of H. Now, my text and therefore my students on their tests are expected to be able to show this work through the addition of vectors in that triangular process off of the origin. So I'm going to just think of maybe the origin being down here somewhere, and we're going to find a position vector for coordinate H. Well, I have to get from the origin, which actually we'll just put it here somewhere. Maybe there's a z-axis, and then there's a y-axis, and a x-axis with that right-hand rule. Let's get from the origin over to E. So we have H, the coordinate, or the vector actually. We're going to find the position vector of this coordinate. Vector OH is going to be the sum of vector OE. And then we need to get from E and add to it another vector going from E to H. And so vector OE plus vector EH is going to give us a position vector of OH. Well, how are we going to do that? Well, we're going to have to do some work here. Okay, we have that the coordinate of G is 1, -2, 3, and we have the coordinate of F, which is 6, 2, 4. And why we're going to, why that's important is if we can set up vector FG. I'll have to erase this work before as we finish this up. I'm going to run out of room. But if we set up vector FG, then because this is a parallelepiped, vector FG is going to be equal to vector EH, and I will be able to finish or write out that portion of the sum that vector OH is the resultant vector, or the sum of vector OE and vector EH. So let's figure out what vector FG is, which is going to be the same as vector EH because they're going to be parallel and have the same magnitude, going in the same direction, and magnitude. Parallel could be like opposite vectors going in 108, separated by 180 degrees. So we have FG, that's where we need to set up FG and not G, F. That would give us a wrong answer. Terminal point minus initial point. So 1 minus 6 is -5. We've got -2 minus 2, which is -4. And then we've got, I'm writing this in a really bad spot. I'll clean this up in a second. G, which is for the Z component, 3 minus 4, which is -1. So I'm going to erase this because I put this in a terrible spot. But remember, FG is equal to, vector FG is equal to vector EH. So we're going to be adding -5, -4, -1. And with that, we're going to add vector OE, and this is just a position vector, and we know what the coordinate of E is, so that is just going to be 5, -1, 3. Go ahead and add these up, and OH is equal to 5 minus 5 is 0. -1 minus 4 is -5. And we have 3 plus -1, which is 2. And we're going to need this, well, this is a position vector. And actually, I haven't answered the question. I can't write this as an answer because if I'm asking for the coordinate of a point, you have to understand there's a difference between the coordinate of a point and a position vector. So while this is the position vector for H, the coordinate for H is going to be 0, -5, and 2. Now, We need that coordinate to finish this problem because now we're going to have to step up and go to the volume. That volume is going to be equal to the cross product, the vector cross product of the two vectors that define the base of a parallelepiped. And we could do all different types of things here. I mean, we could use this as our base and this as the height, if you will, but we're going to keep it in the orientation of the problem and use the points that we're given. And we are going to be using, just highlight this in red, we're going to go ahead and let vector EH and EF define that base. And so we're going to do the dot product of vector cross product of vector EH and EF. We're going to be doing the dot product between that and vector EA. So this vector isn't really defining the height of the parallelepiped, but you saw from our again, our example of where this came from, that it's related to and it works and it's used in the process of finding the height of this parallelepiped. Okay, so as long as you remember how to do the dot product and the cross product, you're good to go. You should probably just pause the video and see if you can't get the right answer. And I am going to, again, review this process with you right now. So we're going to be doing the cross product of vector EH. Now, we have to figure that out. We know what H is, so it's going to be terminal minus initial. So 0 minus 5, negative 5 minus negative 1, which is going to be negative 4, 2 minus 3, which is negative 1, EF. So, oops, forgot my notation. Terminal initial, 6 minus 5, which is 1. 2 minus negative 1, which is 3, and 4 minus 3, which is 1. We're going to dot that with vector EA. Terminal initial point, 6 minus 5 is 1, 0 minus negative 1 is 1, 5 minus 3 is 2. Okay. Again, I just want to double check. It's kind of a long problem. I don't want to carry through a small, silly copy error. All right, we're going to have to get this stuff out of our way. We're going to write out that 3 by 3 matrix to help us set up the cross product. Now, there was no indication of how, again, to set up that cross product. So if this is your first vector, if this is my first vector and you wrote this vector first for setting up your cross product, we're going to have opposite answers. So we're going to go ahead and wrap that instead of absolute value symbols. Looks like almost like magnitude, but yeah. Okay, so we're going to take the determinant of the matrix that we get when we take out the column and row that includes the I, and then minus the determinant of the 2 by 2 matrix that we get when we take out the column and row that include the J. So it's going to give us negative 5 and 1, negative 1, 1. Again, positive determinant, negative determinant, and then back to a positive. Row, column and row that includes the K. Almost running out of room here. We're going to multiply down, negative 4, multiply up and subtract. So it's going to be subtracted by negative 3 as our coefficient of vector I, minus, I do this expansion this way to make sure I don't make a sign error with this minus right here. Multiply down, multiply up and subtract, so negative 5 minus negative 1. Vector J plus, multiply down, negative 15, multiply up, minus negative 4, vector K. Negative 4 plus 3 is negative 1. We've got negative 5 plus 1 is negative 4 with a negative out here, gives us a plus 4J. And then we've got plus negative 15 plus 4 is negative 11. So plus or minus, I'm just going to write minus 11K. Okay, so with that little bit of scratch work here, our vector cross product between these two vectors is -1, 4, -11. We're going to find the dot product between this vector and component form and our vector that's defining or was used in the process of finding the height of this parallelepiped. Keep the absolute value symbols to make sure our volume comes out to be positive. And we have the absolute value of -1 times 1 is -1, plus 4 times 1 is 4, -11 plus, -11 plus 2 is -22, so plus -22. We've got -22, -23, plus 4 is -19. Now here's a perfect example here. My notes are written, so I was just kind of doing this on the fly. I did do these notes as vector EF crossed with vector EH, and my volume came out to be a positive number. This time doing the example on camera, I switched the order of this vector cross product and got a negative answer for volume. That's why we need to keep the absolute value around this, I think it's called a triple product, if I remember correctly, and something I saw online. My book doesn't use that phrase, but I saw it as I was doing some reading for this video and research. This comes out to be a volume of 19 cubic units. I'm Mr. True. Bam! Go do your homework.